All right, here's part 2. We're going to roll through some examples of how to find derivatives of functions involving e to the x, which is pretty straightforward. If you're doing this at the beginning of a calculus unit, there's going to be product rule, quotient rule, chain rule, stuff you may not have seen yet. I don't know, so watch out for that. Anyway, so hopefully you know how to find the derivative of e to the x and other functions involving e to the x, or at least you know that the derivative of e to the x is e to the x. After we do the derivative of 2 to the x, 5 to the x, any constant to an x, we're going to start to say something different. We're going to start to say that the derivative of e to the x is e to the x natural log of e. And of course that simplifies to be e to the x, but that might make more sense soon. Okay, so we're going to find the derivative of e to the power 2x. And, you know, this has the structure of e to some power, which is, well, the derivative of e to some power is e to that same power. That power is 2x, chain rule times 2. We could rewrite that as dy dx is 2e to the 2x, but I don't think I wrote that ahead of time, so we're not going to. The derivative of x times e to the x. Well, this is a product of two functions. I'm going to think of the first function as x, and the second function is e to the x. The derivative of a product of two functions is the first function x, times the derivative of the second, and the derivative of e to the x is e to the x, plus the second function, e to the x, times the derivative of the first, 1. Again, we should probably be rewriting this, and maybe I will. Y prime is e to the x times x plus 1. We typically factor out common factors. The next logical step to find a maximum minimum, which is what we do a lot of times, is looking for horizontal tangents, setting that derivative equal to 0, so we might as well start now. All right, so sine of x e to the x. This is also a product of two functions. Sine of x is the first function, e to the x is the second function. And the derivative of a product of two functions is the first function, sine of x, times the derivative of the second function, e to the power x, plus the second function, e to the power x, times the derivative of the first. How are we going to rewrite this? dy dx is equal to e to the x times sine of x plus cosine of x, which isn't any, I don't know, normal identity that comes to mind, so we'll leave it there. Ooh, a fun one. Okay, or at least not product rule. Or at least not product rule in the easy way. I suppose you could do product rule if we think of this as e to the x squared times e to the 3x. That would work out, and maybe that's a good homework problem. But I see this most easily done with chain rule, and the derivative of e to a power is e to that same power. That power is x squared plus 3x, so chain rule times the quantity 2x plus 3. All right, what do we see here? Very similar structure to the previous one. This is e to the power of sine, so we'll do the chain rule there, and we can ignore that constant multiplier 3. So the derivative of 3e to the sine is 3e to the still sine times the derivative of sine cosine. Well, now we're just getting ridiculous. So the derivative of e to the x is e to the x, but what's the derivative of e to the power of x? Well, this is the derivative of the base e. I guess they're both base e's, but this big one or whatever. And the derivative of that e to a power is e to that same power. That power is another e to the x, which has a rate of change of e to the x. Super weird. Okay. we should probably recombine those, and we have the exact same base e multiplied, so we're going to add those exponents. So the base e with our new exponent, e to the x plus x. Yeah, it's getting silly. Okay, so we're going to take the derivative of this e first, which is e to whatever power it has, and then we're going to do a chain rule, the derivative of this e, which has the derivative of itself to the same power, which means we have another chain rule there. Okay, so the derivative of e to a power is e to that same power, and that power is e to another power, which has the derivative of e to that other power. Notice these two base e's are being multiplied by each other, and that power is in e to the x, which has a rate of change of e to the x. Oh my goodness. That is ridiculous. Okay, so 3 bases e all multiplied. We can add those exponents and get e to the x plus e to the x plus x as our exponent. I think that's the best we can do. All right, last one. How are we going to take the derivative of this thing? Quotient rule. The derivative of a quotient of two functions is the denominator, sine of e to the x, times the derivative of the numerator. And the derivative of e to the x in the numerator is e to the x, minus the numerator, e to the x, times the derivative of the denominator. And the derivative of sine of something is cosine of that same something. That something is e to the x, which has a rate of change of e to the x, all over the denominator squared. So I just decided to do sine squared of e to the x instead of the parentheses.